Hey everybody, welcome to Module 9. We begin talking about hypothesis testing in this module, and hypothesis testing goes hand in hand with confidence intervals as the foundation of inferential statistics. And like I said before, inferential statistics is foundational to research, so there continues to be a ton of value in the material that you're about to cover. So in this video, I'm going to walk you through the structure of a hypothesis test. You'll see things like the vocabulary and things like that. And we're going to do it just by using one example, and it's kind of a fun example that I found at onlinestatbook.com. So it involves James Bond and the idea of, can he really tell the difference between a martini that is shaken or stirred? And so we're going to make up this pretend experiment that never took place, but we're going to pretend that it did, and we're going to look at the results of that and use this to just frame what's going on with a hypothesis test. So here is our made-up experiment. We give Bond 100 taste tests, and each time we give him a taste test, what we're doing behind the scenes is flipping a coin to decide if we should make a martini shaken or stirred. And then we present the martini to Bond, and we keep track of the number of correct responses. Now, going into this, you wouldn't assume that Bond has any superhuman ability. You go into this with the assumption that he's just like everybody else. And so the expectation, if he's just like everybody else, and we're thinking that he does not have this superhuman ability to predict whether a martini is shaken or stirred, the expected number of correct responses would be somewhere in the vicinity of 50. If I went through this experiment, I'm essentially guessing it's one of two things each time out of 100 times. So you're expected to be correct about half the time. So there are two hypotheses going on here. And whenever we have a hypothesis test, you're always going to see these two hypotheses. One of them is called the null hypothesis, where null stands for no change. So you can see I've written here for null hypothesis, there is no change from what is expected. So we would be anticipating him to be correct somewhere in that vicinity of 50 times. The notation for the null hypothesis is H sub 0. And so you're going to see this a lot throughout this module. And so our null hypothesis would be that Bond cannot tell the difference between a martini that is shaken or stirred. But then the alternate hypothesis is really our researching theory in this problem. We're going into this thinking, it seems like Bond, based on all these movies and everything, it seems like he would have this ability. And so this is what we're trying to ultimately accept. We're trying to move on from the null, and we're trying to ultimately reject that he cannot tell the difference so that we can accept the idea that maybe he in fact can tell the difference. And so our alternate hypothesis is going to be H1, and let me scroll down here a little bit, and that alternate hypothesis is Bond can tell the difference between a martini that is shaken or stirred. And so what we do in a hypothesis test is we always begin by assuming the null. And then we're going to collect a ton of data. We're going to do our experiment, get all of our evidence, and then we're going to say, based upon that evidence, is the data extreme enough for us to think the null can't be true and it might be this one? Or is the data not that extreme, in which case we really have nowhere to go? We can't accept the null, we can't accept the alternate. And so this is actually a lot like a trial. And so if we scroll down a little bit more, you can see I've got a few boxes here and we could fill these in. So in a trial, this is how a trial works. You begin with the presumption of innocence, right? And so in a sense, this is like our null hypothesis. So I want you to kind of think of this box right here as we assume the null hypothesis to be true. And then what we do in a trial is we collect data, right? And then based upon that data, we end up with one of two outcomes. And so let me just write here, this is our data or our evidence. And one of the outcomes is the data is very convincing. And so let's say this, if the data, I guess the proper way to say it is if the data are very convincing, if the evidence is very convincing, then we reject the person's innocence. We reject innocence and accept that person's guilt. Okay? Whereas if the data are not very convincing, then we don't say, oh, well, the person's innocent. In the court of, in the eyes of the court, the person would be innocent. But if the data are not very convincing, then it is inconclusive whether the defendant is guilty or innocent. This is exactly what we do in a hypothesis test. We assume our null hypothesis to be true, and then we collect data. The evidence is the data. If the data are very convincing, then we reject the null hypothesis and accept the alternate hypothesis. And if the data are not very convincing, then we say it's inconclusive whether our null hypothesis or our alternate hypothesis is true. And so we really don't know, we don't have much to say if the data are not very convincing one way or the other. One thing I should tell you is we never say, or I should say we never accept, never say that we accept the null hypothesis. So sometimes students think, okay, well, you're either going to reject the null and accept the alternate, or maybe it's the other way around, but that's not true. If the data are convincing, we're going to reject the null and accept the alternate, but if the data are not convincing, we have to say it's inconclusive. We don't know what's true. We don't know if it's the null or the alternate. We just say that we don't have enough data at that point. Okay, so how are we going to do this in the James Bond example? So let's go down here and let's assume the following. So the experiment has taken place. We've given Bond 100 different taste tests, and he's correct 65 out of 100 times. And let's also assume that the standard deviation of the number of correct responses is 5. So a lot of people would look at this and they would say, well, gosh, 65, that's kind of a tough number, right? I mean, a lot of people would think if Bond really has the ability to tell the difference between a martini that's shaken or stirred, he should be way up near 100 or something like that. Or if he's a lot like the other people, maybe he's going to be right near 50. And so a lot of times people might look at this and say, gosh, this is going to make this question a little bit difficult for us. And so what we're going to do is we are going to figure out the following. It's called a p-value. And before you look at that, just listen to what I have to say about it. So in the context of this example, what we're going to find is a probability, assuming that James Bond is just a normal person, so assuming the null hypothesis to be true, we're going to find the probability that James Bond is correct 65 or more times. And so that probability is exactly what a p-value is. A p-value is the probability, assuming that the null hypothesis is true, of observing a value for a test statistic that is as extreme or more extreme than the value actually observed. So here we're saying, what is the probability, assuming that James Bond doesn't have the ability to tell the difference between a martini that's shaken or stirred, what is the probability that he's correct 65 times or more extreme? And so the method to actually calculate this probability is based upon a binomial distribution, and I know that's not something that's been emphasized in this class. And so I'm going to tell you what that probability is. So our p-value in this problem ends up being 0.00176. And so 0.00176 is a very small probability. And so this is saying that assuming the null hypothesis is true, so assuming that Bond really doesn't have the ability to tell the difference between a martini that's shaken or stirred, then the probability of us seeing what we are seeing is actually really, really low. And so it's so low, in fact, that we've got one of a couple of decisions to make. I guess one decision that we could make is we could say, wow, James Bond really doesn't have the ability to tell the difference between a martini that's shaken or stirred, and we just got some really unlikely, he just got really lucky. You could say that, 2 out of 1,000 times, or between 1 and 2 out of 1,000 times, that would happen to somebody who doesn't know the difference between a martini that's shaken or stirred. Or the other option is, you could say, well, no, one of my assumptions must be wrong. And when we're saying one of the assumptions must be wrong, you're saying that null hypothesis must be wrong. And so most likely in this case, given how low this probability is, given how low this p-value is, we would reject the null hypothesis. But we need a framework for rejecting. So let me scroll down a little bit more and talk a little bit about that framework. And so again, we've got our p-value of 0.00176. And here's a general rule of thumb. The smaller the p-value, the stronger the evidence against the null hypothesis. So when researchers are doing these experiments, they're hoping to get p-values that are really close to 0, like what we have here. But technically, to make a decision on whether to reject the null hypothesis or not, these are the steps that you would go through. You would choose a significance level, and this is a cutoff or a threshold that the p-value must go under in order to reject the null. And so just think of a significance level A as a cutoff. And then you're going to compute the p-value as we did. If the p-value is going to be less than our cutoff, we'll reject the null. If the p-value is greater than the cutoff, then we're going to say we don't have enough information, it's inconclusive. And the other thing is, if the p-value is smaller than or equal to that cutoff, we say that the null is rejected at that level, that's the language that we'll use, or that the result is statistically significant at the alpha level. A very common cutoff, common alpha, is 0.05. You see other alphas as well, but this kind of goes hand in hand with 95% confidence interval. Remember how that was a common confidence interval? A common cutoff ends up being 0.05. So in the context of this problem, our p-value is less than alpha because 0.00176 is less than 0.05. So we would reject the null, and if we are rejecting the null, then we can accept that Bond can tell the difference between a martini that is shaken or stirred. And maybe he's not perfect, but he's definitely able to tell the difference more than what an average person would. So this is the general structure. Again, it's null hypothesis, alternate hypothesis, collect your data. If your data is very convincing, and that would be convincing in the form of a very low p-value, because p-value is the probability of observing what you're observing or something more extreme under the assumption that the null is true. So if you have that very low p-value, then that's great indication that we can reject that null and accept that alternate or that researcher's theory. So refer back to this if you get confused about what we're doing in the process of hypothesis testing in this module.